Hi, welcome to Industrial Networking Basics, a series of progressive network design considerations. This series covers networking basics, not so basics, best practices, useful industry networking trends and technologies that every automation professional should be aware of. The first presentation of this series, Basics, Getting Things to Talk, truly covers the absolute basics, and my apologies ahead of time for this being too basic, but it is the core fundamental concepts of networking. Subsequent presentations are going to become more and more involved. For example, the second presentation is going to cover all of the media, copper, fiber, wireless, getting things to talk using the actual media. A lot of pitfalls, a lot of best practices, and things that every user should be aware of. We then step into the topologies, media redundancy, things like RSTP or spanning tree, DLR, MRP, all of the industry standards, why even have redundancy, and how easy it truly is to have media redundancy. We then get into VLANs and segmenting. These are some of the buzzwords currently a lot of users are facing and are rather perplexed with in understanding as to the benefits of this. We then get into network address translation or NATing. This is an aspect of networking that many customers have heard this term, don't understand the core benefit of this, and we too will cover that. We then get into network and device security. Obviously, cybersecurity is a big buzzword in the industry, and we're going to talk about steps that you should take as a user to ensure that not only that your devices are secure, but also that your entire network integrity is secure. We then get into layer 3 in routing. With networks getting larger and larger, there are areas of convergence into the office space. So how do you then take your plant network, converge this into another network, keep it secure, make sure that the IP addressing schemes are unique, and that you only allow certain traffic through. And last but not least, we then get into network management. As mentioned previously, a lot of networks are getting sizable, and you want to be able to maintain oversight of the network and easily be able to manage, maintain, and configure various networking devices. So, that said, let's get started. First and foremost, the absolute basics require breaking down the application in order to arrive at one's networking needs, and ultimately the network. So looking at the hardware itself, one needs to take into consideration the port density, the port type, whether it's copper or fiber, the port speed, is it 10, 100 gigabit, automation protocol considerations. Are there certain protocols that you're running that need to take into consideration certain switch management functionality, such as Ethernet IP, and we're going to talk about that when we address this point. We then also look at the placement of network hardware, and obviously things like segmentation, security, routing, NATing, and so on are going to be covered in some of these subsequent videos. First, port density. This is rather obvious. You simply take the number of devices in the immediate proximity, and those are the number of ports that you're then going to need in order to interconnect them. More often than not, very few people account for spares and the necessary need for uplinks to larger networks. The type of ports, whether they're copper or fiber, are dictated largely by the distance from the devices from each other and the devices to the switch. So anytime that you have a copper segment that is more than 100 meters long, you're going to need to have either another switch in between or converting that over to fiber. So it needs to be known that a solid conductor for twisted pair has a 100-meter limitation, and for stranded conductor twisted pair, this is then derated down to 80 meters. So be aware as to what your pull box of bulk fiber is, and this is then going to dictate the maximum distance that you can communicate. And obviously this is in a very RF EMI free type of environment with properly terminated connections. Fiber, my favorite, has many benefits. It is RFI EMI immune. It does not conform to the 100-meter limitation. It opens up the possibility of running the cabling, in this case fiber, massively, and it makes all of your networking so much easier. It also offers a higher degree of future-proofness, and from a long-term total cost of ownership investment, it really cannot be beat. The only downside to fiber is that the networking hardware itself is going to be slightly more expensive due to the optics that are needed for this. Port speed. Most local device connections only require 100 megabit. Typically you will see 10/100, meaning that the device will auto-negotiate between the two, and only rare instances require gigabit communications to a device. The backbone ports, on the other hand, are a different story because a lot of the data then is being aggregated through a single port, and as a result you then need to have a higher bandwidth capability, and this is where the gigabit ports typically are almost always utilized for backbones. And for backbones, they typically are also always fiber because you're then also looking at a longer distance communication between that switch and the next switch down the line. Protocol considerations, as mentioned previously, are a factor in almost all applications. Some of the most common industrial automation protocols out there is Ethernet IP, Modbus TCP, as well as Profinet. Ethernet IP's communication between the PLC and the drive and or I/O can be multicast. Doesn't always have to be, but it can be, and if not properly filtered on the network, can generate broadcast traffic as a result of this multicast. So multicast traffic is one to many, broadcast is one to all. And on an unmanaged switch network, multicast traffic will be treated as broadcast and will then propagate from one switch to the next, and it is very much akin to a large audience and everyone being on a walkie-talkie on the same channel and 2 or 3 devices having a conversation and everyone getting to hear this. So if not managed or filtered, this multicast traffic will propagate through the network. It's a really bad thing because it can potentially influence the speed of your network and potentially even halt communications. Multicasting is also used by IP cameras. So anytime that you suspect multicast traffic, this is where a managed switch should be used, and multicast filtering, also known as IGMP snooping, be utilized. Also, some devices communicate using SIP sync, and for this they require IEEE 1588, also known as the Precision Time Protocol, for event sequencing and motion control timing to within 100 nanoseconds, which is rather remarkable. There are some proprietary Ethernet-based protocols, such as Profinet IRT, as well as EtherCAT, that require proprietary networking hardware. So this is hardware that actually has an Ethernet chip that supports these protocols. Emphasis here is proprietary, and it's no longer an open Ethernet standard like Ethernet IP, Modbus TCP, and Profinet. Media redundancy. This is dictated by the requirement for network availability. Usually, the larger the application, the greater the need for network redundancy or media redundancy. There are several redundancy protocols, such as RSTP or spanning tree, which I had mentioned previously, DLR, MRP, there's fast MRP, there's HSR, there's PRP. We're going to get into some of these in some of the subsequent presentations, and it's going to allow you to pick one that is best for your application. Next is the placement of network hardware. Consider the cable lengths to the devices and all of the other networking devices themselves. Where would you mount this? Is it going to be mounted on DIN rail, 19-inch rack, or on machine? The 19-inch rack is something that many customers don't think of because they perceive a 19-inch rack switch as something that is IT. There are many 19-inch rack switches that will support industrial temperatures. They're fanless, redundant, powered, AC and or DC, And do keep in mind the availability and access to power, because this too is going to dictate whether you need a 24 volt DIN rail mount power supply or whether you can go directly into the switch with AC, which in a control panel is never a good practice, but nonetheless that availability is out there. Keep in mind the approvals needed for where this is mounted. Is it a class 1 Div 2 environment? Is it onboard? For onboard, obviously you need the EN 50155 standard. For substation automation, it's the 61850-3, and so on and so forth. Keep in mind the ambient temperatures. Just because you have a maximum ambient temperature, say of maxing out at 60 degrees C, consider upping that slightly for your switch needs. With this list of what to look for, a small standalone application with only a handful of devices is rather simple to outline. A larger application is far more complex and best maintained and documented in a spreadsheet. The overwhelming majority of applications at a very granular level contain the following: a controller or PLC, input-output devices. They may contain a workstation, PC, HMI, or some other visual GUI representation of the application itself. Assuming a machine like the one pictured, start itemizing the devices that need to be networked. So in this case we have hypothetically a PLC from Allen Bradley, we have IP67IO from Lumberg, we have an HMI from Maple Systems, KUKA Robot, 2/4 horsepower drives, we have a scale, and just for good measure we have a vision system included in this machine. Breaking this down to the requirements, we have a total of 8 devices. All support Ethernet, obviously this is paramount, and each device's Ethernet port is 100 megabit per second max, so we're going to assume that they're all going to support 10/100 auto negotiating, and several of the devices use Ethernet IP protocol for their communication and their operation. So from a standalone machine, what this means is that you will need a networking device with 8 ports to tie all these into. In this case we have one of the Hirschman switches. This is a spider switch. It has 8 ports. It allows you to simply plug the devices in. It will auto-negotiate to the necessary speed, and devices will start communicating. There's no configuration needed, nothing whatsoever. It truly is a plug-and-play device. So with this unmanaged switch, it will obviously offer this plug-and-play connectivity, but that truly is about it. When connected to a larger network or other machines, it cannot manage this multicast traffic that I'd mentioned previously. It will not offer things like quality of service. Quality of service allows you to prioritize certain communication over the other. You cannot segment the traffic using VLANs. It does not offer any network redundancy or loop protection. It does not offer port control. It does not allow you to enable or disable a port or hard set a port speed to resolve duplex mismatch issues. There are no diagnostics, there's no remote SNMP monitoring, there's no alarming. You really don't get a whole heck of a lot, yet an unmanaged switch is a good, potentially even great solution for a standalone application that is non-critical, non-communication intensive, and is cost sensitive. So aside from blinky lights and a low cost, you really don't get a whole lot else. That said, standalone, you really should not have any concerns in utilizing an unmanaged switch. Do keep in mind, if this is going to be connected to a plant network and you're using Ethernet IP, you could potentially have multicast traffic that's being generated that could then propagate into the rest of the plant network as broadcast traffic. The end customer may require VLANs for segmenting traffic. There's also an issue of IP addresses. Are these IP addresses already being utilized? And this is where NATing comes into play, and so on. Additionally, SIP sync. If this is being utilized, you will need to have a switch that supports IEEE 1588. And this can be translated into a standalone application in almost any industry where devices are used in close proximity. A standalone application is always the easiest to network, but how does one incorporate it into the plant network? And when on a plant network, can other protocols coexist on the same network and same wire? And what about the segmentation best practice that you've heard about? And how does one ensure that everything is secure? And how does one get alerts? And there's just so much more to cover. And for this, please join us in the next presentation as we delve into these topics. Thank you for watching, and have a great day.